So we move to the next talk by Barbara Terhal. She's going to talk about decoding as physics activity.
Yeah, so thanks for inviting me to give a talk. Quantum trajectories is not really the thing that I work on, so I try to choose a topic of my talk that connects to quantum trajectories, because in this sort of toy problem that I'll discuss, we have repeated measurements, and there's going to be some trajectory that we have to infer. But it is a task of decoding, so I'm going to look at some error correction on a so-called GKP qubit. So I'll try to explain what a GKP qubit is, and what this toy model is. And the title is Decoding as Physics Activity, and this is sort of what I want to start with, because I'm sort of suggesting an analogy, and I don't know how deep this analogy is. And so I do quantum error correction, and we have to decode a quantum code. What does that mean? Is that we do repeated measurements to detect errors, and then based on those measurements, we have to infer what happened to the logical information, the information that we care about. So based on measurements, we infer what errors have happened. And that is sort of what we do in physics, right? Based on measurements, we infer what happens in the world. That's basically what we do. And another thing we do then in physics, in theoretical physics, we use gauge series. So gauge series are very widely used, of course, all over the place. And you can ask, well, why do we have degrees of freedom that we actually don't observe, like the vector field? But apparently these are useful. So it's useful to have a theory which describes more than you actually observe. And that's actually what we find in decoding as well. So we assume, so in theoretical physics, we assume that some degrees of freedoms are not observable, but we still use them. And for quantum codes, what you see is we have similar things. Some processes, some errors are actually not observable, they're not detected. They're typically combinations of more elementary errors, and then we say, those degrees of freedom, well, we can call them stabilizers if we use a stabilizer code and all these errors happen on one moment in time. Then it's an error that doesn't do anything on the code space, so it's sort of a gauge degree of freedom. But there are generalizations of that too. It could be a sequence of errors that occur in space-time, so a few at time step 1 and a few at time step 2, and together they cancel. They're such that if I do try to detect the error, I'm not seeing any difference. These are sometimes called space-time stabilizers. And so these degrees of freedom, you can say, well, if a Pauli error happens or not, that is sort of a Z2 degree of freedom, right? It's just, either happens or not, it's 0, 1. But sometimes it can be U1 degree of freedom because it's a phase shift that happens or not, and the strength of phase shift is also variable, is given by some, there's some phase, so it's a U1 degree of freedom. And the latter we see more in codes like a GKP qubit, and so something that uses continuous variable information. So basically, often in order to infer the most likely error, we also use these degrees of freedom, because these are all processes that we don't observe, but they do occur with some probability, so we have to sort of sum over all of them. Okay, so I want to illustrate some of these thoughts in a theoretical analysis that we've done of repeated Steen error correction. I'll explain to you what that is, on a GKP qubit. And this analysis was done in this paper, and then we had an extension. I'll just mention that at the end in a paper, and also in the master's thesis of Jonathan Conrad. Okay, so first explain to you about what a GKP qubit is and what Steen error correction is. And some of you may already know what a GKP qubit is. And GKP stands for Gottesman, Kitaev, and Preskill in 2001. And they put forward a very fascinating idea, is that even though, momentum and position don't commute, you can make two functions of momentum and position, namely you exponentiate them. You take this guy and take that guy, so an operator called SP and an operator called SQ, and those do commute. Okay, why do they commute? Well, this comes about from some commutation. If P, because the commutator of P and Q is proportional to the identity, you can you get them to commute, because this commutator term in principle would put there a phase, but this phase can be 2 pi, and then they do commute. And Q and P here are not really position momentum. What we consider here is we have a single bosonic mode, and P or Q are so-called the dimensionless quadrature operators. So now, how does this code work? We have these two operators that are commuting, and we imagine that there's a +1 eigenstate of both of these. Now, if there's a +1 eigenstate of both of these, in order for this eigenvalue to be +1, it must mean that P is 0 mod square root of pi, and Q is 0 mod square root of pi. And now, furthermore, it's not only that these guys commute, but both these guys can also commute with this guy or that guy. And these two operators mutually don't commute, because you see, if I take the commutator, I have either the I phase, so that's -1. So these can be viewed as a z and an x operator, because they anti-commute. And so this DKP qubit is defined as the common eigenspace of these two operators. And there's two states in this eigenspace. I call one a 0, and the other one I call a 1. And the 0 is characterized for being a +1 eigenstate of this guy, and the 1 is a -1 eigenstate of this guy. Now, this is all nice, but this is highly unphysical, because this says, for example, that I have to make an infinite comb of, in phase space, basically. And these states have infinite energy. So in practice, these code words are more like this, in the sense that here on the left, I have 0, and on the right, I have a 1. And what I have here is I have basically the wave function. So here on the horizontal axis is Q, and here I have the wave function squared. And what in principle, the infinite energy states would be an infinite comb, and there would only be peaks, delta function peaks at even multiples of square root of pi for the 0, because 0 has to be an eigenstate of this operator, which means that Q must be an even multiples of square root of pi. And similar for 1, I have to have peaks at odd multiples of square root of pi. But for finite energy, I can only have finite support in phase space for both 0 and 1. And if I Fourier transform these wave functions, I go to, have their support, I look at their support in momentum space, they also have to have finite support. And the finite support in Q space translates into these peaks having finite width in momentum space, right? Due to I'm just telling you, I'm not showing this, but the fact that you can't have sort of, infinitely sharp peaks in this envelope and have finite support in P space. And you can kind of see that from, Fourier transform. All right, so these are sort of in principle wave functions that people are trying to create in the lab, and there's been experiments on stabilizing a state like this. And now error correction in principle means, well, what are the errors? So for this GKP code, the errors, ideal errors are small shifts. So there's shifts in P or in Q, so translations in phase space. And the idea is that if your shift is small enough, so if the shift strength is less than the square root of pi over 2, which is, in order to go from the 0 state to the 1 state, you have to shift by square root of pi, right? So a shift of square root of pi over 2 is, or less than square root of pi over 2 is less than half of that, right? So the idea is that you you know where you came from. So it's less than half the distance. Now, that's the sort of theory about if you have shifts that are displacements, translations in phase space. But of course, the really typical noise, the experimental noise, is often dominated by photon loss. Then there's dephasing, there are over-rotations in phase space, there are extra-quartic interactions or correlations or cross-Kerr interactions. There's a lot of other stuff going on. So the interest in this qubit is, of course, to say, how well does it actually perform for these realistic sources of noise? Okay, but that's not what we're going to worry about in this talk. This talk really is focused on a sort of an abstract decoding problem, which is not something that's relevant for the experiment, I'm readily able to say, but I find it conceptually interesting. All right, so explain to you a little bit what the GKP qubit is. So what's Steen error correction? So Steen error correction is a method that's used also for multi-qubit codes. And it's something where you have a state, an encoded state, for example, a GKP qubit encoded in an oscillator, and you want to detect errors. So you want to measure, say, these, you want to know whether these shift errors have happened. And what you do, or what you need to do, is you need to create additional encoded qubits. So it's not just you have another single qubit, like a transmon qubit in these experiments are hanging around. No, you need to have another oscillator encoded with the GKP state. And the way this happens, for example, so we look at this circuit. For example, if there are now, let's talk about X and Z errors as if this is just a multi-qubit sort of error correction code. So, so X errors, they propagate down here because they affect this C naught, and then they are detected and corrected here, and they combine, like for example, if there are additional X errors on here, then those X errors combine with the X errors from the qubit that you want to learn, you want to learn something about, and you detect this here, and maybe you do a correction. And similarly, Z errors combine with Z errors on here, and there's a measurement, and you correct it. Okay, so that's the basic idea. The only thing you want to sort of get out of here is that, of course, if I use another GKP qubit that I make in order to, detect errors, that sort of state, makes for an incorrect measurement, right? So the information I get about my error is imperfect, and it may feed back errors back to the data, which is an intrinsic feature of error correction, this type of feature. Now, in my model, we're going to do something like this. We're going to model something simple. Actually, we're going to only, so here you have to correct both X and Z errors. And so in this GKP qubit, this corresponds to correcting both shifts in Q as shifts in P. And we're going to just focus on correcting shifts of this form, either the I, U, P for some unknown U, and this produces a shift in Q. So you have an eigenstate of Q, then it gets shifted, to a different eigenstate in Q by amount U. Okay, so yeah, here you see it's still together, but this is the idea, and the model is going to be fairly simple because all the errors that feed back I can kind of lump into sort of incoming errors. So every QEC cycle, which means every time I couple this qubit with an ancilla qubit and measure something, I also have a round of incoming errors. And I'm going to model these incoming errors as with a Gaussian shift error model. So it's just something where I have a Gaussian distribution characterized by some standard deviation sigma. And, there's going to be shifts of strength U according to that Gaussian distribution. In addition, I'm going to put a similar sort of Gaussian shift error model right before this perfect homodyne measurement. And then the role of that is just to model any errors in this homodyne measurement or model errors that coming out of this sort of prepared state. Now, this is a stochastic displacement model, and it's very far from reality. This is why we did a further analysis a little bit on a model where we just said, can we, do repeated error correction when the error model is only finite squeezing, right? So instead of having these perfect grids with, displacements errors on top, which is wholly unrealistic, we have a model where we have this finite envelope, which you can also model as some coherent error. So it's actually different because this is a coherent error and we're modeling stochastic errors. But like I said, this is just a toy model theory study. And now I want to say something about our method, and this is maybe the interesting part of the talk, our method of decoding versus also what goes on in the lab. And the first thing I want to mention is that maybe what goes on in the lab is really much more, for various reasons, realistic, but still there's a point I'd like to make. So in the lab, in experiments, but also in theory, for example, in experiments in Sivat et al. In Nature 2023, what people do to stabilize the GKP qubit or error-corrected GKP qubit is they have it interact with an ancilla qubit. That's not a GKP qubit, it's just a transmon qubit. And they measure that transmon qubit. And that measurement, they know when, the outcome of that measurement is not perfect. It contains some information about the GKP qubit, and there is an immediate feedback step. And so this is important. So you measure something, you have a QEC cycle, you measure something, and then you do some action on the GKP state to kind of, put back the GKP state in the code space or to stabilize it in the, the form that you like. And so that's sort of modeled here. There's sort of one cycle, there's stuff that goes on here. This is the figures taken from this paper here. It doesn't matter, but there's an auxiliary, there's the oscillator, there's the auxiliary qubit, and there's a measurement going on here, and then depending on the measurement, there's some feedback action. And then they see decay curves in the sense they prepare, like these are decay curves of Pauli operators. So for example, you prepare an eigenstate of Pauli Z initially, and then you do this repeated process, and then this expectation value of 1, say you prepare a Z as 1 eigenstate, that goes to 0 over time, for example, like this. Right, so the point is that in the experiment, they use immediate feedback, taking into account the noise and the measurement, and in the next QE cycle, you measure the correct states. And there's an advantage to using feedback because, well, there's a disadvantage and there's an advantage. The disadvantage is that maybe your feedback operation is also noisy, so you add some noise. The advantage clearly is that, the next measurement you'll do will include what you've done on the system, right? So there's new information coming in that way. Another advantage is that, if your state starts drifting into part of phase space where all kinds of approximations don't hold, you'd rather not be there because then you know that your operations get noisier. So you're really, for example, you like to keep your average photon number as low as possible, centered around 0, right? And so if your GKP state shifts to a higher average photon number, you'd like to push that back. Now, in my model, I have, it's kind of a theoretical model where I have the stochastic phase shift, so it doesn't matter at all. So these are these points. But you can also say, so what we do here is more like what you do for error correction for the surface code experiments, if you know that. You measure for many QEC cycles, and at the end, you measure the whole qubit. And say in the beginning, you prepared either logical 0 or logical 1, and you weren't told which one it was. You only get all these measurement outcomes, and you get the final measurement outcome. And then you have to say, was it logical 0 or logical 1? Right? And that's the game that we play. And so all we care is that we kind of, infer that this final measurement in which we measure all the qubits, that we sort of use all this previous information that we can help to interpret that. Okay, so let's see how this works. Okay, so now the first thing I want to do is to kind of conceptualize this a little more. I'm going to rescale the variables P and Q to sort of variables which are just a rescaling, such that a stabilizer, a stabilizer is stiff, stabilizers are this SP and SQ. They do a shift in P and a shift in Q. And I'm just going to rescale things that one stabilizer maps P onto P plus 4 pi and Q onto Q, and the other one is map Q onto Q plus 4 pi. And a logical is sort of half a stabilizer, maybe you've seen that in the first slide, and it maps P onto P plus 2 pi and Q onto Q plus 2 pi. So if you imagine a torus where there are two coordinates P and Q, then a logical is sort of going once around the torus, if the torus has circumference 2 pi in both directions, and the stabilizer is twice around the torus. Now, what do we want to know? So what is going on with this qubit? Every time this noisy channel acts, it gets a shift. And I'm only looking at shifts, say, in one quadrature, say maybe P, right? And what I really want to know is whether the sum of all these shifts is doing something which is closer to, is close to a logical operation. So it's close to doing an odd number of windings around this torus, right? So if I wind, so the circumference of this torus is 2 pi. So if I round by less than 2 pi, I say, oh, it's winding around 0. If I round with more than 2 pi, or more than pi, it's closer to 2 pi, or so it's between pi and 3 pi. Then I call it logical, right? So the point is to sort of understand there's a cumulative shift that happens because there's a sequence of noise channels, and every time there's a shift, it's going left, right, with random things. And on every shift, I have some information. I have a data point. But that data point is not 100% perfect because there's a noisy channel here. And now I have to sort of, infer what is the overall shift, but not exactly what it is. Just, whether it's closer to, being being closer to this logical action or being, an even number of windings, basically. All right, now one thing is this Q in principle is a homodyne measurement, but we can, in this model, you can just map this measurement on the real axis back to the interval minus pi or pi. You're not losing any information. So that's the sort of the data point that you have. All right, now, okay, so here comes the connection, yes. Yeah, except that it has just a different standard deviation. We just have a different parameter, but it's the same. It's a stochastic displacement channel. Yes, exactly. Yeah. All right. So if I'm asked, so now we said, okay, what's the problem? What is the optimal strategy you can think about? So we're not doing any feedback, right? Every time we have a measurement here, we're not asking to correct for anything. We just collect data. So there's a cumulative shift. And we have to infer this sort of, what is this cumulative shift at the end? Is it close to this logical action or not? And so this cumulative shift, so the shift after sort of, after the first round is phi 1, and then it's phi 2, and it's phi m. So, first there's no shift, and then finally there is some shift that is actually fixed by last measurement. I assume the last measurement is perfect. And so what we have to do, so there's two strategies which are common in decoding problems. One is a maximum likelihood, which is really say, what's the most likely trajectory of this, of these values, basically. And the point is, I have what the points I have, the data points are these measured things. So I don't know these values, I just have to infer some trajectory over time. Now, a sort of an often more efficient strategy is what's called minimum energy inference. So you determine the path of minimal energy. Now, what do you say? Well, energy, what's my sort of energy function? And I'll give that in a moment. So you determine the path of minimal energy of a function, and it's given the data. And so that path should give you that k here. This k is odd or even. Okay, so how do I get my h? And the h is sort of like an equation of motion in this. Well, h is really like a Hamiltonian. This gives you the equation of motion. And one can derive, so the data are the sequence of measurements, q1 to qm minus 1. And you can derive that this Hamiltonian is this. And this Hamiltonian also has a sort of an intuitive picture in the sense that it has two terms. One is what you could see as a kinetic term. And this kinetic term, so maybe you just recall, sigma is the standard deviation of the Gaussian noise model. So if sigma is very large, there is sort of a lot of noise. And so this has very small, this term is very small. And so, okay, maybe I shouldn't say. So basically this model, it plays the role of inertia in this model. And this plays a role of sort of a random potential. And also the depth of the potential, the scales with this sigma m, which is also very intuitive. Like if sigma m is very small, means the standard deviation is very small, means that the measurement is very accurate. It pins the value of this cumulative shift by measuring qt. Basically, you learn about this value by measuring qt. So you see, there's actually nothing quantum going on here, but this is because of our error model having nothing quantum. If you want to understand how this goes, actually, it's just sort of what you say. What you have to do is you say, okay, given the measurement outcome, what's the probability that I measure 0 at the end? Well, what's that probability? Well, I have to integrate over all this, the sequence of values. This is a sort of a path integral, because I have to integrate over the values for the cumulative phase shift of phi 1 and phi 2, etc. And at the end, I have to be in an interval, which I call I0, which is sort of when the final phase shift is, closer to, not doing a logical action. And I1 is the complement interval where the phase shift is close to having a logical action, so it would flip 0 to 1, basically. And you can manipulate this path integral. This is how you get the Hamiltonian. This, you use Bayes rules, you drop the Q, and then you would just define this. And this is something, given the shift, what's the probability for Q, that you get out of your error model. And so you can evaluate that and get an expression that is like this. All right, now, so what we did in this work is we took that Hamiltonian that we've constructed and we run some numerics. We say, okay, what's the extreme and what's the minimum of the Hamiltonian? That gives some kind of equation of motion, and this actually is a studied model. It's called the Frenkel-Kontarova model with a random quench potential. And what is the randomness? That's these measurements, right? These measurements Q at time t, they're all just samples from this sort of Gaussian distribution. At least, you know, well, you have to, including the error that comes in from the data qubit. And you'd like to have a way of starting at some point, you know, t is 0, to integrate this forward, you know, given q of t, what's the point later? And this is what you see here. For example, here on the left, we have measurement outcomes, or if you can read this, which are these stars. And so, you know, in the first round, we measure a q that, you know, the q lies in between minus pi pi. This is a 2 pi, so this is the interval minus pi pi. Or so maybe I should say the green interval is sort of the logical 0. So the point is to estimate the trajectory. At the end, we estimate this phi m here. And if it lies in the green interval, we say it's a 0. If it lies in the red interval, we say it's a 1. And all we have to do is, depending on these points, which are these stars, we have to integrate this trajectory and see, does it land in green or does it land in red, right? That is the task of decoding. And so here in green, you see the real trajectory based on our simulation. And here in the top, it doesn't actually matter that much, but we have found 2 optimization methods to estimate this trajectory based on these data points, right? So we do some optimization that integrates this equation forwards in time, basically, to estimate, you know, whether we land in the green part of phase space or in the red part of phase space, where we would call it, you know, a logical flip has happened, right? So that's sort of, because, you know, in the logical phase space, we are winding and do an odd number of windings around the torus approximately. In the green part, we do an even number of windings around the torus. And this is what we have to estimate. This phi, you know, goes on, sort of go around this torus, and how does this trajectory go? Okay, yes.
So the measurement outcomes are guaranteed to be in the first green strip, right?
Yes, exactly, because they're mapped back on these things.
The
yeah.
trajectory may be 2 pi away from that.
Yeah, indeed, but we can map it back. But the cosine, because the cosine function doesn't care about this, so you can map it back in this interval because it will be the same value. The potential will be the same value. Yes. Right. All right. Okay, so this is just a toy model. There's no experimental realization of this setup. And I also don't, you know, because this displacement model is kind of, you know, a toy model. I don't necessarily advocate doing error correction this way. I mean, one of the things is also the C0 gate is not so easy to realize, but there's other ways, you know, the C0 you use for Steen error correction. There are alternatives called Knill error correction that use beam splitters that may be more feasible. But there's also something that you could still, this picture, so what I don't know, for example, in the Sivak et al. In the Nature experiment, they did this immediate feedback. And then at the end, they measured the logical, and that's then the outcome. Then they say, okay, but actually they could do one more step. They could say, given, and then it gets more complicated, given all the measurements I do, and the feedback I've done, should I now measure this as a logical 0 or measure as a logical 1? So, and the final measurement. So, and they haven't done that in the experiment. I don't know whether to give them something extra. Do you understand? So they could use, the problem is that when you do stabilization, so when they do feedback, that computation becomes more complicated. I think it becomes much more nonlinear, right? Because you interact with the system and your next measurement will depend on this. So the dynamics that you have to simulate or approximate is going to be more complicated, right? So, so I don't know what that will give. But the point is, of course, that for the surface code, this is, we never do stabilization. And there's a good reason for it, because if I have a multi-qubit code, I can't stabilize it locally. That we know that error correction, if we try to do this, well, there is a way of decoding that way, but it's very complicated and it has a very poor threshold, because decoding is a much more non-local process on the whole surface code lattice. Whereas here we encode a single logical qubit in a mode, and in principle we could stabilize it. But maybe it's an interesting question how you would, what kind of equations of motion do you get if you do include this feedback in terms of, what is the optimization problem then you have to solve? It probably gets very hard, because already we saw that if you have the coherent squeezing noise, so I wanted to look at whether our strategy made any sense if we'd had coherent squeezing noise, like what is now, now there's not a stochastic accumulation of shifts or something. And then the problem is that it's sort of you're tracking the wave function itself. And we had some Green's function, and there's a path integral, and then actually you could say, well, this path integral I can approximate by a single trajectory. But that's sort of a classical approximation. But in our case, this is all in Conrad's thesis, the path integral may also have interference between paths. So a single classical path is not optimal. So the point is you get into sort of this point that in decoding at some level is reconstructing the quantum dynamics, but maybe not every aspect of it, because this would be hard. We'd need a quantum computer to do this. But it does pose a question a little bit, whether there's, what kind of limits do we have on decoding? Because decoding is a classical thing, right? Decoding is estimating the logical trajectory in a classical fashion. Whereas if that comes about from quantum dynamics, how far can we be off? And I don't think this has been very well explored, because, there are not many experiments of this repeated error correction or these ways of trying to, decode many, many rounds for these bosonic qubits. Yeah, and I kind of like this thing because it's a sort of similarity of what we do in physics, where you say, oh, it's a quantum dynamics, and then, we make a classical approximation from the path integral and so on. So it has a certain appeal in that sense, but maybe it's just an analogy. Yes, how am I doing on time? Okay. Okay, that's it, what I want to say, so thanks.
Questions?
It's okay, yes. Yes, thank you for your wonderful talk. Can we compare this with a quantum filter? Because you have all the measurement, all the things, and in theory, I will say, you can update the density operator, so the quantum state. So
yes.
Is it possible or not to compare this kind of decoding with respect to the best decoding that you can imagine is to use the quantum filter?
But yeah, okay, so I don't quite know what a quantum filter is, but of course, if you update the whole density matrix, then you simulate the whole system.
Yes, yes.
Right?
Something.
And so the problem with decoding is that you'd like to know something about the trajectory without knowing all the details of how the density matrix evolves.
Yeah. Yes, to see.
And is that what the quantum filter also does? Because you would like to reduce the space, you'd like to simplify, make some simplification.
Just to compare, because the optimal way to decode is to use the quantum filter. And then just to compare how far from the optimal you are.
Yes, yeah, that's true. Yeah, I agree. I mean, if it's
just this, it's just not to, in practice, to do this.
No, I agree. I mean, yeah, if you just update the density matrix and you keep track of it. But of course, that gets, if you have now many GKP qubits, and then it gets very complicated. Yeah. For one, it's possible, yes.
It should be possible.
Right,
but for
and you could compare, indeed.
It would be a nightmare, I guess.
You could compare whatever approximation you have with the actual trajectory, indeed.
Yeah.
Yes, yeah, exactly. No, I would, well, in the end, so in the surface code experiments, for example, they prepare all the qubits in 0 or all in 1, say, and then they measure. So it's actually, you prepare in logical 0, logical 1, you do many rounds of measurements, you measure all the qubits at the end, and then you just have to infer, was it a 0 or a 1 that I started with? Yeah, so it is actually very similar.
Okay.
Yeah?
So there isn't multiple error possibilities that I need to map back to, and
Well, it's less here in the sense that not here it's continuous shifts, right? So I have to keep track of sort of the shift value that accumulates, and of course in the surface code I have errors that happen in many places. In that sense, it's different. But the final, it's finally you have to estimate 1 bit, but what it depends on is different. Yeah.
Okay, so maybe I ask this as a general question. So suppose I had these multiple options, then does one know what kind of classical dynamic? So it seems like you map this to a classical dynamical system, right?
Yeah.
So would one have such a mapping possible in that case as well?
You mean for the surface code?
Yeah, yeah.
Yeah, no, I think the thing is with the surface, well, no, well, the thing is there are also ways, maybe, you know, like when the surface code, no, well, it depends on what your error model is. You could have continuous measurement, like not measurement the outcome is 0 and 1. So that gives sort of a potential, so that, but the point is, of course, we try to discretize it to, you know, either having Pauli error or not. And in principle, you could say, well, if I have amplitude damping, what, you know, maybe there's another parameter, or, but it doesn't come, here it comes naturally, right? Because it remains that for just multi-qubit codes, it's generated by X, Y, and Z errors, right? But here's the generators are displacements of different strengths. So it is intrinsically continuous.
Okay, yeah, thanks.
Yeah, so I didn't quite understand the Hamiltonian that you wrote. I mean, so, I mean, is it just something you want to sort of minimize and, but it's, and the equation, so QTs are the measurements, right?
Yes.
And, but yeah, so is this just an optimization problem? That's how you...
Yeah, so what we do is we construct this Hamiltonian because it relates to the maximum likelihood problem. And the maximum likelihood problem is something we say, you know, what's the most likely value of this last thing given all my measurements, basically. And what I actually reconstruct, I construct the whole, well, and I try to get this via reconstructing the whole path. And this, there is in this maximum likely problem, every path has a certain probability associated, and the probability you're just going to write as, you know, as with a logarithm, like this kind of thing. So here I have, for example, this thing. So the probability, if I had a set of phase shifts at points in time, what's the probability to measure something? That is something I know. I can just estimate. It has a Gauss, it's just a Gaussian basically. And then I just take the log of this, and if I work this out, and this cosine actually comes about from the fact that from some periodicity. This is actually sort of a Villain approximation. Yeah, so there's an approximation that I'm doing. But maybe that doesn't answer your question.
Okay, so, and then you wrote some dynamics which,
so I'm finding, I'm trying to find, indeed, given Q, I'm trying to find the sequence of, you know, this is a vector, so I'm trying to find this whole sequence that minimizes this, given that I start at phi 0 at 0. And the goal of that is then to actually find this value and find whether, you know, whether sort of K, you know, yeah.
So, and then it's some kind of gradient minimization, is it with Hamiltonian, but with the Hamiltonian?
Yeah, then that's the Hamiltonian, but the problem is how do you minimize this? This is actually not an easy model. So this has been, so this is the extreme, you can like say the derivative is 0, and then you get this type of equation. I don't actually remember this, but then we try to numerically integrate this approximately, and that's what we call forward minimization. And we look at then the performance of this, how well we...
Okay, but if it's strictly Hamiltonian dynamics, it would conserve the energy, right? So I mean, how would it...
It would what?
It would keep H constant. So maybe you have a dissipation, is it? I mean, like, otherwise...
No, there's no... Okay, so it's not Hamiltonian dynamics. Maybe that is confusing to say. There is a Hamiltonian function, which is a cost function. And that cost function is relevant because we're choosing, we say the most likely trajectory is one that minimizes the cost function. That is the idea. And how do I minimize the cost function? I can take a look at, you know, where its derivative is 0. And so that gives me sort of an equation of motion.
So I'm wondering if you have some quite precise measurement of Q, so it's a small error in the measurement. Can you have some kind of linearization that would allow you to do least square?
Some kind of what, linearization?
Yeah, linearization of the models that
Yeah,
gives
well, you can,
least square
yeah.
estimation.
Well, you mean, you can say that you can
This is small, and
approximate the
so
potential, yes, yeah. Yeah, indeed. But we were more interested in, well, I mean, it's also, the point is, many people for this GKP qubit take models where the measurement is perfect, and then they derive sort of, they infer things from it, and I think that's very far from the actual sort of situation. So in a sense, it's more interesting to have, yeah. Well, we in this paper, actually, we did look at limits for like encoding a GKP qubit and then do a surface cone on top, and then we did look at these types of limits also. This, yeah, when sigma m is very small.
Other questions? If not, then let's thank the speaker again.
Thank you.